An Evolving Gravity Model, From Quantum Asymmetry to Planetary Dynamics by Johannes Benyashibo. 2 Introduction. Challenging the constant for centuries, gravity has been treated as a fundamental, unvarying force of nature, mathematically described by constants like Newton's Gn, or geometrically by the fabric of spacetime in Einstein's theory. Yet, this perspective rests on a foundational assumption: that gravity has remained constant throughout the universe's history and across all scales. This book embarks on a journey to challenge that assumption. Born from the intuition and independent research of the author, it proposes a radical alternative. Gravity is not a fixed constant, but an emergent property that evolves over time, driven by dynamic processes at the quantum and planetary scales. The initial spark for this inquiry arose from a simple, yet profound question: why do we assume gravity has always been constant? This question led to a deep exploration, moving beyond the conventional view and seeking a new appendices framework where gravity could emerge naturally from deeper physical principles, rooted not in unchanging constants but in the interplay of quantum scale imbalances and internal energy redistribution within celestial bodies. The conventional understanding faces challenges when confronted with certain empirical observations, particularly the geological record of the early Earth, which suggests a weaker gravitational pull than today's 9.81 ms2. Standard models struggle to reconcile this without invoking improbable scenarios like a significantly less massive early Earth. This observation became a cornerstone, shifting the inquiry towards the possibility that gravity could have increased over time, rather than remaining constant or decreasing. This paradigm shift necessitated identifying the drivers of such an increase. The exploration led to a profound realization: gravity might not solely depend on the amount of mass, but also on how asymmetric that mass is at the quantum level and how efficiently this asymmetry is locally managed or restored through internal processes. This insight culminated in the proposal of a new, dynamic formulation for gravitational acceleration g. G equals new appendices A are m are 2I2 here. A represents the local baryon asymmetry, which is hypothesized to increase with mass accumulation. R is a crucial new term: the energy restoration rate, representing the rate at which the local symmetry is healed through particle ejection processes. M is the planetary mass and R is the distance from the center. This formulation replaces the assumption of a universal constant with a dynamic interaction between quantum vacuum fluctuations, nuclear processes, and the ongoing evolution of the celestial body itself. The initial intuition that gravity increased over time found a compelling mechanism in the internal dynamics of planets, particularly those massive enough to undergo nuclear fusion. As mass accumulates, local baryon asymmetry grows, potentially increasing gravity. However, as fusion begins within the core, converting hydrogen to helium, a critical process governed by the Pauli exclusion principle comes into play. Not all hydrogen can be compressed and bound into helium due to this fundamental quantum new appendices mechanical constraint. This results in the release of unbound hydrogen atoms. This released matter acts as a restoration agent, effectively reducing the net local asymmetry and contributing to the R term in the proposed equation. Thus, gravity doesn't increase indefinitely. It rises initially as mass accumulates and asymmetry grows, but then stabilizes as the onset of fusion and the subsequent Pauli-blocked hydrogen release provide a self-regulating mechanism. This leads to the core hypothesis: gravity evolves dynamically, not from hypothetical dark matter or exotic forces, but from the intricate interplay of known physics operating at quantum and planetary scales. This book will delve into the foundations of this emergent gravity model, building upon concepts from entropic gravity, thermodynamics, and cosmology. It will detail the derivation of the proposed law, explore the feedback dynamics between asymmetry and restoration, apply the model to Earth's history and contemporary phenomena, and discuss potential astrophysical and cosmological implications. We begin by laying out the conceptual framework and the journey of thought that led to this novel perspective. New Appendices: Foundations of an Evolving Gravity Model. Chapter 1: Rethinking the Origins of Gravity. My journey into this question began not within the confines of a traditional academic institution with prescribed research paths, but as an independent researcher. This perspective offered both challenges and unique freedoms. Without the pressure to conform to established dogma or pursue funding for incremental advancements, I had the liberty to question the very fundamentals. It allowed me to follow my intuition down paths that might otherwise be considered unconventional or even speculative. This independence was crucial in formulating a hypothesis that challenges one of the most deeply ingrained concepts in physics. The standard laws of physics treat gravity like a fixed force, governed by Newton's constant Gn, or later described geometrically by Einstein. The gravitational acceleration g we experience on Earth is calculated based on Earth's mass and radius, multiplied by this seemingly immutable constant Gn. But what if gravity isn't fundamental in that sense at all? What new appendices if it's not governed by constants, but instead emerges and evolves naturally from deeper physical principles? Principles rooted not in static constants, but in quantum scale imbalances and internal energy redistribution. This fundamental questioning led me to propose a new formulation, a law that attempts to capture the dynamic nature I suspected gravity possessed. It's a formulation that replaces the assumption of a universal constant with a dynamic interaction between quantum vacuum fluctuations, nuclear processes, and the ongoing evolution of the celestial body itself. G equals A R M R2, where G is the gravitational acceleration at time t, A represents the local baryon asymmetry at time t, essentially, the imbalance between matter and antimatter concentrated in a given region, like a planet. R is a crucial 3 new appendices. Chapter 1. Rethinking the origins of gravity. Novel term. The energy restoration rate at time t. This represents the rate at which symmetry is healed or restored locally, which, as I came to realize, involves specific physical processes leading to particle ejection. Ms. The mass of the celestial body. Ris. The distance from the center of the body. Paleontology, and even analyses of ancient raindrop impressions. These diverse fields offered intriguing, albeit indirect, evidence suggesting that Earth's gravity might have been weaker in its distant past, perhaps around 9.1 ms2 or even lower, compared to today's 9.81 ms2. Classical models struggle mightily to explain this without resorting to the improbable assumption that Earth had significantly less mass in its early history, which contradicts robust data on planetary accretion. So I asked, could gravity have increased over time, not decreased or remained constant? If so, what physical process could possibly drive that increase? This question became a central focus of my exploration. For my intuition began with an observation that seemed at odds with the constant gravity paradigm. I had been reading about early Earth geological records, new appendices months. I delved into various areas of physics, looking for a mechanism. The breakthrough came when I arrived at something profound. Gravity is not just about how much mass you have, as the standard model dictates. It's also, and perhaps more fundamentally in its local manifestation, about how asymmetric that mass is at the quantum level and how efficiently symmetry is restored through internal processes within that mass. This gave rise to the core idea that forms the backbone of this book. Mass accumulation during planetary formation leads to an increase in local baryon asymmetry, A, compared to the average cosmic asymmetry. This concentration of asymmetric matter enhances the gravitational pull. As the planet grows more massive, internal pressure and temperature rise, eventually initiating nuclear fusion in the core, specifically, the fusion of hydrogen into helium. However, due to the fundamental quantum mechanical principle known as the Pauli exclusion principle, not all hydrogen nuclei under pressure can bind and fuse into helium. Pauli exclusion prevents identical particles from occupying the same quantum state. This limits the efficiency of the compression needed for fusion. The critical new appendices consequence is that some hydrogen atoms are released or kept in a state where they effectively reduce the net local asymmetry that was built up. This released matter acts as a restoration agent, actively healing the local baryon asymmetry. This restoration process defines the R term in my proposed equation. The interplay between the growth of asymmetry and the increase in restoration means that gravity rises initially as asymmetry builds, but then stabilizes as the restoration process becomes significant. Thus, in this model, gravity evolves dynamically not from mysterious dark matter or exotic, undiscovered forces, but from known physics operating at the most fundamental quantum scales and the observable Plan-Etary 5 scale. Tracing back how these ideas connected, I recall reading Eric Verland's work on entropic gravity, which proposed that gravity could emerge from entropy gradients. This resonated deeply, suggesting gravity wasn't a fundamental force but a thermodynamic consequence. But it left me asking, new appendices, where does this entropy, this fundamental drive for gravity, actually come from? Then I looked at Ted Jacobson's thermodynamic derivation of Einstein's equations, showing the deep link between the laws of gravity and thermodynamics. Again, brilliant work, but it still felt like it described how gravity behaves thermodynamically, without specifying the physical mechanism that generates the necessary thermodynamic potential or entropy gradient in the first place. So I turned to cosmology, thinking about the universe's large-scale structure and its properties. Cosmologists speak of a small but crucial baryon asymmetry in the universe, the reason we have matter at all instead of just energy. And I thought, if the universe has an asymmetry, why wouldn't smaller concentrations of matter, like planets, also exhibit significant local asymmetry? From there, the pieces began falling into place. I explored how this local asymmetry could grow and become highly concentrated due to mass accumulation and differentiation processes inherent to planetary formation. And finally, the crucial connection emerged. I linked this growing local asymmetry to nuclear fusion occurring in the cores of sufficiently massive celestial new appendices bodies and, critically, to the Pauli exclusion principle. This principle explained why fusion wouldn't simply consume all the available hydrogen perfectly. It showed how hydrogen release during fusion could provide the physical mechanism for restoring symmetry locally and, therefore, preventing infinite gravitational growth. This is where my independent research converged, where the questioning of a fundamental assumption, the observation of geological anomalies, the exploration of emergent gravity theories, the concepts of cosmic asymmetry, and the details of quantum mechanics and nuclear physics coalesced into a unified, testable framework for gravity as an emergent, evolving phenomenon. This book is the detailed exploration of that framework. 6. Chapter 1. Rethinking the Origins of Gravity. Chapter 2. Entropy-based and information-theoretic gravity. In the preceding chapter, we introduced the core premise of this work, that gravity may not be a fundamental constant force, but rather a new appendices emergent phenomenon that evolves based on local conditions. This perspective aligns with, and seeks to build upon, existing theoretical frameworks that have similarly challenged the fundamental nature of gravity by linking it to concepts from thermodynamics and information theory. While these theories offer powerful insights into the nature and behavior of gravity as an emergent effect, they often leave open the question of the underlying physical source that drives this emergence, particularly at the scale of individual celestial bodies. This chapter will review key ideas from this domain, setting the stage for how the proposed model of asymmetry-driven, restoration-modulated gravity provides a potential physical mechanism for this emergent behavior. The notion that gravity could be deeply connected to thermodynamics gained significant traction with the pioneering work of Dr. Ted Jacobson in the mid-1990s. Jacobson demonstrated that Einstein's field equations, the cornerstone of general relativity describing spacetime curvature and gravity, can be derived by applying basic thermodynamic principles to local causal horizons in spacetime. The core idea involves treating spacetime horizons, such as those surrounding black holes or Rindler horizons experienced by accelerated new appendices observers, as thermodynamic systems. By applying the Clausius relation, which states that changes in entropy are related to heat flow divided by temperature, i.e., ds equals dqt, in the context of these horizons, Jacobson showed that the flow of energy across a local horizon implies a relationship equivalent to the Einstein field equations. In this framework, gravity is interpreted as an enthalpy or thermodynamic force arising from differences in spacetime temperature, where spacetime it's 7-8 Chapter 2. Entropy-based and information-theoretic gravity self seeks to achieve thermal equilibrium. The curvature of spacetime, which we perceive as gravity, becomes a manifestation of this thermodynamic drive. This approach provides a powerful link between general relativity and thermodynamics, suggesting that the laws of gravity might be statistical in nature, emerging from the collective behavior of microscopic degrees of freedom of spacetime itself. Building on this, Dr. Eric Verland proposed in 2010 the concept of entropic gravity. This model suggests that gravity is not a fundamental force mediated by gravitons, but rather an emergent force arising from differences new appendices in entropy or, more fundamentally, information associated with the position of matter. Drawing inspiration from holographic principles, which posit that the information content of a volume of space can be encoded on a boundary or screen, Verland argued that matter approaching a holographic screen changes the amount of information on that screen. The change in entropy associated with matter's position, combined with the idea that systems tend towards states of higher entropy, gives rise to a force that behaves precisely like Newtonian gravity. In this entropic gravity model, gravity is seen as an entropic force, analogous to osmotic pressure or the force exerted by a polymer chain seeking a state of higher conformational entropy. It is driven by the universe's fundamental tendency towards maximum entropy, or more accurately, towards states where information is distributed in a way that minimizes gradients. The gravitational pull experienced by an object is thus a consequence of the entropic pull towards regions of higher information density on a hypothetical holographic screen. This perspective offers an elegant way to derive gravity from information-theoretic principles, suggesting a deep connection between information, new appendices entropy, and the gravitational interaction. Both Jacobson's thermodynamic gravity and Verland's entrop-IC gravity frameworks offer profound insights by demonstrating that the familiar laws of gravity can be understood as emergent phenomena arising from underlying thermodynamic or information-theoretic principles. They move away from the idea of gravity as a fundamental interaction force and instead present it as a collective effect of more fundamental processes related to the statistical behavior of spacetime or information. These models successfully reproduce key features of gravity, providing strong theoretical support for the concept of emergence. However, from the perspective that led to the present work, a critical question remains less explicitly addressed within these frameworks. While they beautifully describe that gravity emerges from thermodynamics or information, and how it behaves in response to entropy information gradients, they are less specific about the fundamental physical source or mechanism that generates and sustains the required entropy gradients or information imbalances in the first place, particularly in the context of localized masses like planets and stars. Where does the fundamental potential that drives this thermodynamic or entropic emergence originate physically? What are the specific microscopic or new appendices quantum processes that give rise to the macroscopically observed gravitational effect? This is precisely where the emergent gravity model proposed in this book 9 diverges and seeks to provide a complementary perspective. We posit that the fundamental physical driver, the engine behind this emergent gravitational potential, is the local baryon asymmetry that accumulates within celestial bodies. Furthermore, we propose a specific physical process, hydrogen release during nuclear fusion, governed by the Pauli exclusion principle, as the primary mechanism for the restoration of this symmetry. By identifying local baryon asymmetry as the physical source of the fundamental imbalance linked to gravitational potential, and the fusion-driven restoration as the process modulating it, this model aims to provide the underlying physical mechanism for the emergent gravitational phenomena described by theories like Jacobson's and Verland's. It suggests that the thermodynamic drive or entropic gradient is directly tied to the concentration and dynamics of asymmetric baryonic matter. Thus, this book's framework seeks to bridge the new appendices gap by offering a concrete physical basis for the emergent properties of gravity, placing the dynamic interplay of quantum-scale asymmetry and its restoration at the heart of this fundamental force. The following chapters will delve into how this concept is formulated into a testable law and the dynamics it predicts. 10 Chapter 2. Entropy-based and information-theoretic gravity. Chapter 3. Baryon asymmetry and spacetime curvature. In Chapter 2, we explored theoretical frameworks, such as those by Jacobson and Verland, which propose that gravity is an emergent phenomenon arising from thermodynamic or information-theoretic principles. These models offer compelling descriptions of that gravity might behave as a consequence of entropy or information gradients, but they often prompt the question regarding the fundamental physical origin or source of these gradients. This chapter introduces a core hypothesis of the present work, that local baryon asymmetry, amplified through the concentration of matter, serves as this fundamental source, directly new appendices linked to the manifestation of spacetime curvature or gravitational potential. We begin by considering baryon asymmetry on the cosmic scale. Observational cosmology indicates that our universe is composed predominantly of matter rather than antimatter. The ratio of baryons to photons is approximately 6:1010, indicating a minuscule but crucial excess of matter over antimatter that survived the early annihilation phase. Without this slight primordial baryon asymmetry, the universe would consist almost entirely of radiation and not the galaxies, stars, and planets we observe today. This cosmic asymmetry is a fundamental property of the universe, its origin still a subject of active research in particle physics and cosmology. Now, consider the formation of celestial bodies through the process of gravitational accretion. As vast clouds of cosmic dust and gas collapse under their own gravity, matter is drawn together, concentrating enormous quantities of baryons into relatively small volumes. While the initial cosmic medium possesses a uniform low level of baryon asymmetry, the processes of gravitational collapse, condensation, and subsequent internal differentiation within forming planets and stars can lead to a significant increase in the local concentration of new appendices this asymmetry. As matter clumps together, any initial non-uniformities or segregation processes could theoretically lead to regions with 11-12 Chapter 3. Baryon asymmetry and spacetime curvature, a higher effective baryon asymmetry than the cosmic average. Furthermore, internal processes like core mantle differentiation, phase changes under extreme pressure, and potentially even sorting effects on trace quantities of particles with different fundamental properties related to asymmetry could contribute to structuring the internal distribution of asymmetry within a formed body. The central hypothesis advanced in this model is that this local concentration of baryon asymmetry is the fundamental physical driver underlying the gravitational effect. We propose that the presence of a significant local imbalance between matter and potential symmetry-neutral states creates a fundamental stress or potential in the vacuum energy or the structure of spacetime itself. Conceptually, one can view a region of high baryon asymmetry as a departure from a perfectly new appendices symmetric, potentially lower energy vacuum state. This departure generates a gradient that spacetime seeks to smooth out, and this smoothing manifests as what we perceive as gravity or spacetime curvature. In this framework, the term A in the proposed gravity law, G equals A RM R2, quantifies this local baryon asymmetry. It is conceived as a factor that represents the strength of the gravitational source originating from the asymmetric nature of the mass m. Unlike the standard model where gravity's source is simply mass energy, here, it is the quality of that mass in terms of its asymmetry, modulated by its state of restoration, that determines the gravitational influence. The mass m is still present in the equation because the total amount of asymmetric matter is relevant, but the effectiveness of that mass in generating gravity is scaled by A and R. This perspective offers a distinct